Okay, today we have second derivatives and their graphs. So what we learned on Thursday was first derivatives and their graphs. So we found all the pieces of the first derivative, the critical numbers. We created a Sine chart and we found local maximums and minimums, and we were able to sketch the original function based on the characteristics of the first derivative. Well, we're going to do the same exact thing today, but with the second derivative. So we're going to find the second derivative, set it equal to 0, solve for x, make a Sine chart, and these new points will be called inflection points. And inflection points deal with concavity. So first derivative deals with max and mins. Second derivative deals with concavity. So first page is all about definition. So let's get through that first. Okay, number one, the graph of a function is concave up on some interval AB if the first derivative is increasing on the same interval. So what that means is that, looking at the chart below, if the second derivative is positive, this means that the first derivative is increasing, which means that the graph of the original function is concave up. And examples of a concave up graph look like this. This is what concave up looks like. Okay, so if the second derivative is positive, the original function is concave up. 2, you are concave down on the interval AB if the first derivative is decreasing on the same interval. So that's also in this chart, where if the second derivative is negative, the first derivative is decreasing, the original function will be concave down. And concave down looks like this. Okay. And here I say, remember, from last class, to determine where a function was increasing or decreasing, we took the derivative, we solved for x, and we created a Sine chart. Like I said, we're going to do the same thing for the second derivative. Okay. All right. So next, it is important not to fuse concavity with falling and rising. A graph that is concave up may be falling, rising, or both falling and rising on the same interval. So we're just saying not to confuse. So if you say you're concave up, that doesn't mean you're always increasing. Being fully concave up is the first graph we see here. This is all concave up. And if you're concave up, then you could be decreasing and increasing on the same interval. And the same could be said for a graph that is concave down, which is picture number 2. A graph that is concave down may be increasing and decreasing on the same interval. So we see that we increase and decrease. I guess don't confuse the terminology. If you're concave down, that doesn't mean that everything's decreasing. Concave down means you could be increasing and decreasing for a function. Okay, or for a graph. Okay, that is concavity. So the second derivative deals with concavity. And in order to find concavity, well, we must find something called inflection points. So first derivatives had critical numbers. Second derivatives have inflection points. And an inflection point is where concavity changes on a graph. Concavity may go from concave up to down or concave down to up. But in order for an inflection point to be an actual inflection point, concavity must change. The sign must change. Okay. So theorem 1, inflection points. If f of c is an inflection point of the original function, then c is a partition number for the second derivative. So kind of is the same as the first derivative. Critical numbers were called partition numbers because they broke up the Sine chart. Inflection points are also partition numbers because they're going to break up a Sine chart that we make for them. So some similarities there. Okay. Important to note, partition numbers for the second derivative are only candidates for inflection points. The function must be defined at the inflection point x equals c, and the second derivative must change sign at the inflection point of c in order for the graph to have an inflection point. So what all that means is that when we make the sign chart, if the signs change, then our inflection point is a candidate. If our signs do not change, then our inflection point or our partition number is not an inflection point. So signs must change in order for it to be an inflection point. And of course, I'll show you what all that means as we work through this next example. But any questions so far? Oh, that definition, right? What was that?
No questions.
Okay. So example 1, we want to find the intervals and where we are concave up, concave down, and we want to find out if our inflection points are actual inflection points. So given this function, h of x equals negative x to the fourth plus 28x cubed minus 28x plus 3, what we're going to do is find the second derivative. Okay. And my laptop doesn't want to keep up. Hang on, it may have broke. One moment. Yep, my laptop lost connection to Zoom. Yeehaw. Let me pause the recording for a second then. Oh, yep. Okay, so step A is find the second derivative. So let's go through that. So to get to the second derivative, of course, we have to take the first derivative. So the first derivative of the function above is negative 4x cubed plus 3 times 28. What is that? 84. Let me see. Yep. 84x squared minus 28. And then we take the second derivative and you get negative 12x squared plus 84 times 2, 168x. Okay, so we found the second derivative. The next step is we're going to take our second derivative, set it equal to 0, and solve for x. So here's step B. Take h double prime of x, set it equal to 0. You get negative 12x squared plus 168x, set it equal to 0. And I hope I can take out a 12. I can. So I'm going to factor out a negative 12x, and that'll leave me with x minus 14 equal to 0. And then set both terms equal to 0, and we'll get x equals 0 and x equals 14. Okay, so these are the x values from the second derivative. So these are going to be called my possible inflection points.
Is this example 1?
This is example 1.
Huh.
Why? What's up?
No, I just got kind of confused, to be honest. I think I might have printed out the wrong one.
Oh, I said I updated the notes. So here, I posted it earlier, but if you just logged on, then you don't see the notes I posted. So let me see. There you go.
Okay, so I need to go print out this one.
Exactly.
Okay.
Okay, so after we find the inflection points, the possible inflection points, we are going to plot them on a sine chart. So I think this is still step B. So I'll say sine chart. And there we go. There's negative infinity. There's positive infinity. And then here's 0 and 14. Next, we make our intervals. And our intervals are from negative infinity to 0, 0 to 14, and 14 to infinity. Okay, and now we pick test numbers. Give me a test number from negative infinity to 0.
-1.
-1. Give me a test number from 0 to 14.
1.
1. And give me a test number from 14 to infinity.
15.
15. Perfect. Okay. This is a sine chart for the second derivative. So you must plug into the second derivative. Oh, it's actually labeled H.
Yeah.
So H double prime of X. So H double prime of -1, H double prime of 1, and H double prime of 15. All right, Desmos, here we come. Let me hide this, move that over, go to Desmos, and then let me type in the second derivative, -12x squared plus 168x. All right, do my table feature, and then come back to my test numbers. And just like the first derivative sine chart, we don't care about the number. We only care about the sign. So when I type these numbers in, -1, 1, and 15, we see that at -1, I get a negative answer. At 1, I get a positive answer. And at 15, I get a negative answer. Okay. Now looking at the sine chart, what this means is that from negative infinity to 0, I get a negative output no matter what number I pick. From negative infinity to 0, the answer will always be negative. So this means that we're negative and we will be concave down. So negative and concave down. Or I can even draw a little picture there. This is what concave down looks like. Okay. And then from 0 to 14, no matter what number we pick, we'll always get a positive output. So this means that you'll always get a positive number, which means we're concave up, which will look like something like that. And then from 14 to infinity, no matter what number we pick between those, you'll always get a negative number. So this means, again, we are concave down. All right. And now we can answer one of our questions. It asks, where are we concave up and where are we concave down? So all we do is look at our sine chart to answer this. I guess I can call this part C. Yeah, I can call this part C. Let me do that first.
Okay.
So C, we are concave up on what interval?
negative infinity to 0 and also 14 to positive infinity.
That'd be down, but good, good. So concave down from negative infinity to 0 and 14 to infinity.
Correct. And then 0 to 14 is concaving up.
0 to 14 is concave up. Okay, so we found our intervals of concavity. Okay. So that's going to be one answer. Next, we want to know, do we have inflection points? So remember, I labeled them as possible inflection points. So by the theorems, by the definitions on the other page, in order to be an actual inflection point, the sign must change. So I'll call this step D, inflection points. IPs. And first inflection point we'll look at is 0. Okay, so we look at 0 and we see that the sign to the left of it is negative and the sign to the right of it is positive. Did the signs change?
Yes.
Yes.
Yeah.
Also, you can look at the concavity. We went from concave down to concave up. So again, the signs have changed. This means that x equals 0 is an inflection point.
What about 14?
We're getting there.
Oh, okay. Yeah.
Well, tell me about 14. Do the signs change at 14?
Well, yeah, the same thing happened.
We go plus and
Minus.
minus. Good. So since the signs change, this means that 14 is an inflection point.
And then we just plug them into h of x, right?
Exactly. Good.
Yes.
See, repetition is key, just like last time. So now that these are inflection points, we have to find the point of inflection. So like he said, you must take these and plug them into the original function. So take these, plug into h of x. So we'll get h of 0 and h of 14. All right, and back to Desmos. I need the original function as well. So let me get that original function that's up there and type it in. Negative x to the 4th plus 28x cubed minus 28x plus 3. Do my table feature, and then we're going to type in these values, 0 and 14. Hey, 0's there already, and I'll just make that 14. Oh, wow. 0 gives me 3, and 14 gives me 38,027. All right. These are your points of inflection. This is where the graph will change direction. It'll go from concave up to concave down or concave down to concave up. All right. So remember that these are points. So I'll write them as such. This is 0, 3, and 14, and 38,027. Okay, so let me make this graph pretty so we know what we're looking at. So my x-axis goes from, I'll make it go from, that's probably good. And my y-axis, we're gonna go from, let's say negative 100 to 38,030. Oh, wow. And my x values, I start at 0 and I go to 14. Why not? There we go. This is what we're going to be looking at for our sketch. Okay. So I'm going to graph this just by plotting the points of inflection and using my sine chart. So I have 0, 3, and 14 and 38,000. Oh boy. Okay. So this would be 0. And I can go by twos. 2, 4, 6, 8, 10, 12, 14. And then this is going to be fun. I'm just going to say that this is 3. And this will be 38,000. Because again, it's just a sketch and it doesn't have to be perfect. So my 2 points are 0, 3, which is going to be right there. And then 14 and 38,000. Okay. Now I'm going to graph by using the sine chart that we created. All right. So what we're saying with the sine chart is that from negative infinity to 0, we are concave down. So I'm going to start at my point of 0, 3 and draw concave down. That's what concave down looks like. And then by my sine chart, it says from 0 to 14, we are concave up. So I'm going to go from my point 0, 3 to my next point 14 and 38,000. And this is what concave up looks like. Not that curvy. There you go. That's concave up. And then from 14 to infinity, we are back to concave down. So we go concave up and then we curve right back around. And that's concave down. And done. Mine looks cooler than the one on the left.
Question.
Go ahead.
So what difference is there between this one and the one we did last week?
So last week we were graphing using max and minimums. So remember, first derivative does critical points and maximums and minimums. Second derivative, what we're doing today, does inflection points and concavity.
Okay.
So that's the main difference. We're graphing by concavity and inflection points today.
I got a quick question, Professor.
Go ahead.
In B, can you remind me how you got 0 on negative 12x? I just
good. No, you're good. So we set both of them equal to 0, right? So if you set negative 12x equal to 0 and you want to solve for x, you would divide by what?
12. Negative 12.
Negative 12.
Gotcha.
And 0 over that is 0. No, that's a good question. So that's how we get that. Cool.
Yes, sir.
All right. Okay. Let's see.
What difference is there between the notes that I guess I printed earlier in the day and the notes that you just posted right now?
They're longer.
The ones that you posted.
The ones that are in Canvas already, I mean, I've been using those for years, but this is only an hour and 15-minute class. So if I did those ones, we'd be here for a while. That's why I changed them up. I removed some problems and I was like, okay, maybe it'll make it a little long. This still is a long lesson, even though I cut out information.
All right. I guess I'm going to have to go print those out tomorrow then and have to rewatch the lecture because I don't have a printer here.
Yeah, all good. Why won't this erase? All right, my technology is hating me today. It's not even the end of the week. All right, I'll erase those later. Okay. All right, the next example is called curve sketching. So we are so to curve sketch, we use something called the graphing strategy, and it's a couple of steps. The first step is strictly algebraic. You find the domain and the X and Y intercepts. Step 2 is everything we learned on Thursday. In step 2, we're going to take the first derivative. We're going to solve for x. We're going to make a sign chart, and we're going to find max and minimums. So if you missed out on Thursday, well, all of Thursday fits into this tiny step, which is actually a lot. And then step 3, we're going to do everything we've learned today. We're going to take the second derivative, set it equal to 0, solve for x, make a sign chart, and find concavity and inflection points. And then once we do step 1, step 2, and step 3, we are going to take step 4 and plot everything on this graph. So buckle down. This is going to be fun. All right. So we'll start with example 2. Step 1. So given the function 3x to the 4th minus 18x squared, let's go ahead and find this domain. So lucky for you guys, since you're in business calculus, the easy calculus, you will only be given polynomial functions. And what is the domain of all polynomial functions?
All real numbers.
All real numbers. Hey, that's so easy, right? So the first thing is the domain of this function, which is going to be negative infinity to infinity. Perfect. No matter what, you're going to get a polynomial. You're not going to get anything else other than that. My regular Cal 1 will suffer. Okay. So B, let's go ahead and find the X-intercepts. To find an X-intercept, you let f of x equals 0 or y equals 0, the same thing. So we take this function, 3x to the 4th minus 18x squared, set it equal to 0, and factor to solve for x. All right, I can take out a what?
The 3x squared.
Good, 3x squared. That'll leave me with x squared minus 6 equal to 0. Now we can't factor anymore, so we're going to set both terms equal to 0. 3x squared equal to 0, x squared minus 6 equal to 0. On the 3x squared, you'll divide by 3, and you'll get x squared equals 0. And then you'll square root both sides, and you'll get x equals 0. On x squared minus 6, we're going to move the 6 over, square root both sides, and we're going to get x equals plus or minus the square root of 6. Now, since we're going to be graphing these x-intercepts, we actually need to know the decimal number for the square root of 6. So let me just type that in on my calculator I have here. And the square root of 6 is 2.45. Okay. And I think when you're doing this on my math lab, it wants just the x values. It doesn't want you to type it as a coordinate. So I think these, what I boxed, will be your answers for MML for my math lab. But since we're graphing it, I like to put these into coordinate form. So your x-intercept and y-intercept are going to be 0, 0, square root 6, 0, and negative square root 6, 0. So those are our x-intercepts. Okay. And then C, find your y-intercept. This one's always the easiest. You let x equal 0, which means I get f of 0. I plug 0 into this function above for every x, and that becomes 0, and that becomes 0. So my y-intercept happens also to be 0. So you'll get the point 0, 0. Okay. First step is done. Purely algebraic, no calculus involved. Any questions on that?
For part C, we only do that to the first point.
For part C, since you're finding a y-intercept, you plug 0 in for every single x.
Every single x.
So it would be 3 times 0 to the 4th minus 18 times 0 squared but none of that matters because it all becomes
Oh, got you. Okay.
0. Okay. Now moving on to step 2. We're about to do everything we did on Thursday. So let's go ahead and find the first derivative. Let me zoom out there. And the first derivative is going to be f prime of x, and it's going to be 12x cubed minus 36x. 12x cubed minus 36x. Okay. So zoom in more until I can't zoom in anymore. Perfect. So for this step, we take the first derivative. We set it equal to 0. So we take 12x cubed minus 36x. We set it equal to 0. We solve for x. What can I factor out?
12.
X,
X.
right?
Love it.
Good. So that leaves you with x squared minus, what's that, 3?
Yeah.
Three.
Yeah, x squared minus 3 equal to 0. Okay. And then we're going to set both terms equal to 0. 12x equals 0. X squared minus 3 equals 0. And we're going to get x equals 0 for the first one. That's easy. Over here, a little more work to do. X squared equals 3. You're going to square root both sides. Good. And then you're going to get x equals plus or minus the square root of 3.
But do you want the exact decimal there or no?
We will if, I mean, yeah, we're going to do it because we're probably going to have to graph these anyways. But
1.73.
1.73.
Yes, sir.
Cool. Okay. And these are called your critical numbers.
Yeah.
So now we're going to take these critical numbers and put them on our sign chart. That's our next step. All right. Let me just look at something really fast. Oh, whoops. When I did this in my other class, when I took out 12, I said that was x squared minus 4. Well, it's x squared minus 3. Okay, so here we do our sign chart. I'll do it in blue, sure. And I'll plot my critical numbers. Negative square root of 3, 0, and square root of 3. Here's negative infinity. There's positive infinity. Next is my intervals. And negative infinity to negative square root of 3. Negative square root of 3 to 0. Zero to the square root of 3 and square root of 3 to infinity. Next is test numbers. We're going to have 4. X equals, X equals, X equals, X equals. And give me a number from negative infinity to negative 1.73.
Negative 1.
That would be above 1.7.
sorry.
Negative 2.
Negative 2. Good. Give me a number from negative square root of 3 to 0.
Now we could do negative 1.
Now you can do negative 1. 0 to the square root of 3.
1.
1. And square root of 3 to infinity.
2.
2. Good. This is a sign chart for the first derivative. Plug into f prime of x. F prime of negative 2. F prime of negative 1. F prime of 1. And f prime of 2.
Desmos.
Desmos for the win. Give me that first derivative. 12x cubed minus 36x. And then table. Here we go. Plug in my test numbers. All right. Then over here. What are you doing, Desmos? There we go. All right, -2 is in there. Perfect. -1 is in there, or it was in there. -1. And then 1, and then 2. Okay. Once again, we don't care about the number. We only care about the sign. So it looks like we have negative, positive, negative, positive. Which means we'll come here. And remember that first derivative only deals with increasing or decreasing. So this means that if we're negative, this means that we are decreasing. Positive means we're increasing. Negative means we're decreasing. Positive means we're increasing. Okay, which means we can find, or we can answer the question for what are the intervals of increase or decrease based on this sign chart. Let me move that. Okay. So increase and decrease. And looking at the sign chart, we have increase on -√3 and 0, and √3 to infinity, and then decrease on -∞ to -√3, and
0
good,
√3.
0 to √3. There's our increase, decrease. And now we have to find maximums and minimums.
All right, there's
Ooh,
a minimum at.
man.
Oh, sorry.
Let's say max and mins. Okay, let's look at the first number. X equals -√3. You decrease and then you increase. Is that a max or a min?
Local minimum.
That is a local minimum. And then let's look at 0. 0, you increase, decrease. That is a
Local max.
local max. And the last one, x equals √3. You decrease, you increase. So again, we have a local
Minimum.
minimum. But we want to find the exact location. So
You got to plug it in.
we plug these into the original function. F of -√3, f of 0, and f of √3. Here we go. Now I need the original function, which is right there. 3x to the 4th minus 18x squared. Table, come here. All right, -√3. So √3, 0, and √3. All right, so I get -27, 0, and -27. Perfect. These are my maximums and minimums. Perfect. Okay, there it is. That was everything we did on Thursday into one step. Any questions on that? So seems pretty repetitive, right? Okay, so now we move on to step 3, where we do what we learned today. We are now going to take the second derivative. So there's the first derivative up there. So f double prime of x, it's going to give me 36x squared minus 36. Okay. Zoom in and set it equal to 0. F double prime of x equals 0. So 36x squared minus 36 equal to 0. I can factor out a... Actually, no, we don't have to factor anything out.
Well,
I can move the 36 over. I mean, you could factor it out. We'll still get the same answer, but I'm going to make this a little faster. We're going to move the 36 over, divide by 36, and we're going to get 1.
and then now the square root.
Square root both sides, and we get x equals plus or minus 1.
The square root of 1 though, right? Or just 1?
Well, what is the square root of 1?
You're right.
All right. So since this is from the second derivative, these are called my possible inflection points, my pips. They're not actual inflection points until we prove them on the Sine chart, which comes next. Intervals, test numbers, 3 of them. 1, 2, 3, and negative infinity to negative 1. What's a good test number?
-3.
Negative 3. Why not? Negative 1 to 1.
0.5.
You're just throwing all the ones out there. All right, that works. I would have chose 0, but 0.5 is in there. And 1 to infinity?
2.
2. Yeah, I like it. As long as it's within the interval, you can use it. So those are good numbers. All right. Sine chart for the second derivative. So plug into f double prime of x. F double prime of -3, f double prime of 0.5, and f double prime of 2. You know what time it is. Give me that second derivative right here, 36x squared minus 36 to my table right there. And we're typing in -3, 0.5, and 2. All right, zoom in here. Again, we don't care about the number, we only care about the sign. So we are positive, negative, positive. All right, which means that from negative infinity to -1, we're positive, which means we're concave up. From -1 to 1, we're negative, which means we're concave down. Then from 1 to infinity, we're positive, so we are concave up. Which brings us to answer intervals of concavity, concave up, concave down, and only concave up on negative infinity to -1 and 1 to infinity, concave down from -1 to -1. Now we have to look at inflection points. Let's look at the first one at -1. -1, does the sign change?
Yes.
It goes positive to negative, which means -1 is an inflection point. Let's look at the next inflection point of 1. Does the sign change?
Yes.
Yes, negative, positive. So 1 is an IP. And this means to find their exact location, we plug them in to the original function. F of -1, F of 1. Whew. All right. And I think we still have the original function up. Get rid of that. Come up here. That's the original function. So there's -1 and 1. They're in there already for me. All right. So -1 and 1 gives me -15 and -15. Cool. These are the points of inflection, and I get -1, -15, and 1, -15 as my points. Okay. So let me make this graph appropriate. I need to look at all my y values. I have 0, -27, and -15. So the lowest I'll go is -30. And the highest I'll go is 0. So that means I'm just going to put like 10 here. My x values, I have 0, -√6, -√3, and -1. So I'll just say -5 to 5. Let's see how that looks. Beautiful. There it is. Okay, now we have to do that on our graph. So square root of 6 was 2.45, and square root of 3 was -1.73. Okay, so the first thing we're going to plot are my x-intercepts and y-intercepts. So that's what I'm going to do down here. X-intercept was at 0, 0, which is right there. And then it was at 2.45 and -2.45. So around there. Those are my x-intercepts. My y-intercept was at 0, 0, which is plotted already. Now we're going to plot our maximums and minimums. -√3 and -27, 0, 0, which is plotted already, and square root of 3 and -27. So -√3 is 1.73. So I have to make my intervals appropriate. Since it's -27, I'm going to do these by threes. 3, 6, 9, 12, 15, 18, 21, 24, 27. And of course, all negative. Okay. So square root of 3 was negative 1.73. So that point's going to be probably down here. And then square root of 3 was 1.73. I'm going to put that there. So there's my max and minimums. Let me label that. These are my minimums. And this is my max. Okay. Last thing to plot is the inflection points, -1 and -15, 1 and -15. So 1 and 15 right there, -1 and 15 right there. Okay. Whew. We're ready. I have everything plotted. And now we're going to just graph by our concavity sine chart, which is right there. You can probably barely see it, but it says from -∞ to -1, we are concave up. So this is what we look like. We come down and actually, whoops. Yeah, we come down. We hit this and do that. All of that is concave up. And then from -1 to 1, we are concave down. So we curve around like that. That's concave down. And then from 1 to infinity, we're back to being concave up. And there it is. And that is the curve sketching graphing strategy using the first derivative, the second derivative, and the X and Y intercepts. Definitely a process, but it's a repetitive process. Any questions on that?
Only 2 questions for tonight's.
What was that?
Only two questions for tonight's homework.
Oh, yeah. Yes, maybe.
I have a question.
Go ahead.
Going back up to where you were at when you were trying to find the second, what's it called? The second what? The second F, I guess?
The second derivative.
In the second derivative, sorry, yes. When you're trying to find that, how is it that you come up with the 36x to the second power minus 36? Because the first one,
exactly, we're looking at the first derivative and we're taking the derivative of that to get the second one.
oh, okay. Well, I'm looking at my notes. I don't think my notes match, but I just got the ones that you posted right now too.
Mm-hmm.
I don't know if I got the wrong ones or what's up.
We'll see if we get you the right form in a second.
Okay, thanks.
Yeah, those should have been it though. MML says I made them yesterday. So you're good. I mean, if you look at the top of the page, if you have that function 3x to the 4th minus 18x squared, then it's the right paper.
What's 18 squared? Okay. Okay, got you.
Got it?
So
right.
pretty much when you're finding the second one, you're just going to add on to where you already found the first one.
Exactly. So you have the first derivative, and then you're going to take the derivative of the first derivative to give you the second derivative.
Okay, got you. Yeah, sorry, my mistake.
You're good. All right. All right, last one, guys. An actual application. All right. Example 3. The marketing research department of a computer company used a large city to test market the firm's new laptop. The department found that the relationship between price P dollars per unit and the demand X units per week was given approximately by P equals 1296 minus 0.12x squared on the domain of 0 to 80 laptops. Okay, weekly revenue can be approximated. So they're giving us the revenue function. So revenue is always known as X times P. Well, we take this value of P and plug it in here and distribute the X. So our revenue function from the marketing or the research department is now given as 1296x minus 0.12x cubed. So we're going to take this revenue function and we're going to find maximums, a maximum or a minimum for this function. So A says find the local extrema. So remember, to find local extrema, to find max or minimums, we will take the first derivative. First derivative gives us maximums and minimums. So that's what we're going to start with. For A, we're going to say R prime of X, take the derivative of the revenue function they're giving us, and the derivative of 1296x is 1296 minus the derivative of 0.12x cubed is going to be 0.36x squared. Good. So now, remember, to find maximums or minimums, you take the first derivative and you're going to set it equal to 0. So we have 1296 minus 0.36x squared. We set it equal to 0 and we solve for X. I will add the 0.36x squared to the right side. And then I'll divide by 0.36. And 1296 divided by 0.36 gives me 3600 equal to x squared. Square root both sides, and you'll get plus or minus 60. Okay, but we're talking about a business model here. So which value do we not include?
The negative.
The negative. Good. We only take positive 60. This is my critical number, which means the next part is, unfortunately, a sign chart. But this sign chart is a little easier because they're giving us restrictions to stay within. What two X values are we stuck between?
0 and 80.
0 and 80. So when I make this sign chart, I have 0 and 80. And I just plot my 60 right there in the middle. And all we want to know is this 60 going to be a maximum or a minimum? So we have our intervals. 0 and 60, and 60 and 80. And then we'll do our test numbers. From 0 to 60, what's a good test number?
30.
30. All right, all right. From 60 to 80, what's a good test number?
7.
70? 70?
Yeah, 70.
All right. And you're going to plug these into the first derivative. So it's going to be r prime of 30 and r prime of 70. All right. I'm just going to use my calculator here. I don't think we have to switch to Desmos for this one. So 1296 minus 0.36 x squared. And I type in 30 and I type in 70. So when I do that, I get a positive number and a negative number. Okay, so this means that from 0 to 60 will always be increasing. And from 60 to 80, we will be decreasing. And all this is asking us is to find a local extrema. So this means if you look at 60, we increase and then we decrease. This means that 60 is a local
Max.
max. That's it. I looked at the MML homework and I don't think they want you to plug it into the original function. They just want you to say, where's your local max at? And you say X equals 60. Okay. Any questions on that one?
No.
No, no more. All right. Last one. This one says find concavity, which means we are now going to take the second derivative. So we'll have r double prime of x, and the derivative of 1296 is 0, but the derivative of 0.36x squared is going to be negative 0.72x. Okay. And you take your second derivative, you set it equal to 0. And you solve for x. You divide by 0.72, and x is going to be 0. Here's my pip. Okay. Next is sine chart. But again, what restrictions are we stuck on?
We don't use negatives.
Well, 0 negative.
No, but it's nothing.
We're still stuck on the interval of 0 to 80. And it just so happens that our possible inflection point is also an endpoint for our sine chart.
Oh
So
no.
no, it's not bad. This means that the only interval we have to work with is from 0 to 80. So that's our interval here. 0 to 80, which means just pick a test number in between there.
1.
1. Perfect. And you plug that into the second derivative, and we don't even need a calculator for that. You plug 1 into here, and the answer is going to be positive or negative.
Negative.
The answer will be negative, which means that if this is negative, you are concave down from 0 to 80. Okay. So all this question wants to know is what intervals are you concave up and concave down? Will this function ever be concave up?
No.
No. Right? No. So concave up, we say none. And concave down, we are from, yes, 0 to 80. There you go. That's it. Done.
Would look better with a